Welcome to the third lecture. Today we will talk about applications of composite. So, at first we will see some of the primitive types of composites and their use, and then we will talk about the modern applications of composites, especially the ठीक है आरेक बार शुरू करूँ ना okay. Welcome to the third lecture of this week. We will talk about applications of composite today. At first, we will talk about the applications of some of the primitive composite types, and then we will look into the applications of fiber reinforced plastic composites, which is what is that is this course about. So, if we look at the kind of composites which were used in the older days, the first one that comes up is wattle and dove type composites. So, this was there at around 6000 BC. So, this was a wall building technique. We can see a picture over here. We can see that there is a skeleton that is generally made of flexible woods like hazel, willow, and so this has a type of lattice structure, I would say. So, this gives strength. So, it is a kind of reinforcement, and then a sticky mixture of clay, soil, sand, straw and animal dung is smeared over that. So, we can and that is called dove. So, this dove is matrix, and this wattle, that is that lattice, wooden lattice, is can be considered as reinforcement here. So, this is a type of a primitive type of composite, and then in around 3400 BC there were plywoods made in the by the Mesopotamians. So, they used to glue layers of wood using animal glue. Some of these descriptions can be found in these links. Then in Egypt there was something called cartonnage, that is a funerary material. So, that was formed by layering linens and papyrus soaked in plaster. So, we can see a mummy here that is wrapped with this cartonnage, and that is painted. Then Romans started building concrete from volcanic ash, and they used to call it opus cementitium, and that was made of volcanic ash, lime water and piece of rock, tile and brick. And then Mongols made archery bows made of tendons, horns. Now, let us look at some of the historical developments up to up to what we see today. So, first synthetic resin was developed at around 1870 to 1890. Then Portland cement came in 20th century. First artificial fiber reinforced plastics bakelite came in 1907. Polyester was made in early 1930s. Composite wing spars. So, spar is an important part of a wing, we will talk about it later. That was made by Howard Hughes at around 1940s. Then composite got its application in water transport also. In 1942, fiberglass and polyester resin was used for making boats. So, polyester resins are better corrosion resistant. So, that is why it is used in applications where exposure to water is involved. Then Kevlar was used for body armor, that was also at around 1966. Then automotive and infrastructural use came at around 1970s. Carbon nanotube came into use in 2000, early 2000. Now, carbon nanotube is a nanomaterial which has excellent properties. So, that kind of revolutionized. So, with the use of these carbon nanotubes, composites can be higher strength can be imparted to composite. Then in the field of composite manufacturing, we got some revolution at around 2010 with the use of 3D printed composites. Now, let us look into some specific applications. We will talk about space application first. The first example is Webb telescope. Now, this telescope has a backplane structure, and this backplane structure maintains high precision. It holds the mirrors. So, it has to maintain high precision so that the mirrors are oriented properly. but that is not an easy job because these telescopes suffer from huge temperature variation. So, that is where fiber reinforced composite comes into play, because we have seen that FRP have high dimensional stability. So, they have lower temperature expansion coefficient, thermal expansion coefficient. So, that is why where dimensional stability is involved with temperature variation, fiber reinforced plastics are used. So, that is why we see the use of carbon fiber reinforced polymer and other advanced composites here. And apart from that, it gives the other advantages like high strength and low mass. Then this telescope have a sun shield structure that is generally made of layers. So, it has 5 layers. Now, between each layer heat is reflected and finally, it is emitted out. So, that is what each layer does, and so this part is generally the hotter part. It is exposed to sunlight, so it gets heated. Now, the goal is not to is to prevent the heat from coming to the colder part. So, this is the colder part. So, that is these layers are made of composites, and also the secondary mirror support structures also have use of composites. Then comes satellite. So, satellite has primary and secondary structure frames, bus, trusses, and composites are used there to ensure structural integrity. So, during launch these structures suffer from high vibration, and we have seen that composites have high damping. So, it damps out the vibration quickly. So, because of that composites are used here, and also it helps in maintaining alignment of electronic and optical systems due to high thermal stability. Then there are deployable antenna arms and dish support structures which needs high dimensional precision. So, that is why composite is used here. Then electronic and payload support structures, optical benches, battery cages, sensor mounts. So, due to the non-magnetic and non-conductive property of composites, composites are used in this application. So, this avoid electromagnetic interference. Now, let us see some of the aircrafts. Now, Boeing 787 Dreamliner that has a capacity of more than 250. So, this is a big aircraft that is long haul aircraft, mainly fly in international routes. So, that has 50% composite by mass, and it has 80% composite by volume. So, you can say that see here that something which is contributing to 80% volume is contributing to only 50% mass. So, that is a huge saving. So, if I compare with other aircrafts like Boeing 777 has only 12% composite, and this one has around 50% composite. So, this pie chart shows the use of various constituents. So, composite is around 50% by weight, aluminum 20%, titanium 15%, steel 10% and other materials 5%. And we can see the use here. So, this is carbon fiber. So, we have seen that carbon has higher modulus and higher strength. So, carbon fiber is there in most of the part. In some part only we have fiberglass, and then we can see where other materials like aluminum and other materials are used. So, composite helps in weight reduction by around 20%. Now, because of less weight it burns less fuel. So, it burns around 20 to 22% less fuel as compared to Boeing 767 and other jets which are used for long haul routes. Now, because of using less fuel, so it delivers it emits less CO2. So, around less 20% lower CO2 emission is there, and also finally it achieves around 30 to 40% reduction in life cycle emission including manufacturing and operation. More details can be found here. Airbus 350 is also a long haul aircraft, and that has around 53% weight of composites. So, that is the highest composite application in any commercial jet. Primary composite material is carbon fiber reinforced polymer, and there are that is mainly used in primary and secondary structures, and other than that in some parts there are GFRP, and also hybrid laminates like glare is used in some of the localized region. So, we are getting a new term glare, and that is glass laminate aluminum reinforced epoxy. So, it has benefits of both aluminum. So, when I talk about the benefits of aluminum duct these benefits of this metal. So, ductility is one benefit. So, it has benefit of both aluminum and FRP. So, it is used in some parts of Airbus A350. So, there is large single piece composite fuselage construction. So, that reduces the number of fasteners, and application of automated fiber placement and resin transfer molding ensures consistent quality and high speed of manufacturing. And there is sophisticated bonding techniques is used in place of riveting. So, when it is fabricated using purely aluminum, we get so many rivets. With composites, number of rivets is reduced significantly, and we have other kind of joints, and with large piece construction we can further reduce the number of joints. This table shows the use of various composite materials in various parts of the aircraft. In fuselage, it has CFRP. So, the entire fuselage is made from carbon fiber reinforced composites using out of autoclave and automated fiber placement technique. In fact, mostly it is CFRP as we have seen, and same in Boeing 787 also. Wings upper and lower skins have CFRP. So, it gives proper aerodynamic shape, and actually when we make some lifting structure, maintaining proper aerodynamic shape is crucial. And with composites, because it can be molded, because making different shapes is possible with molds in composite. So, with composite it is easier to get that kind of shape than metal. Wing spars and ribs are made of composite. Those are major load bearing component. So, if I look at a cross section of a wing, it looks somewhat like that, and then so this is the cross sectional view, and across that there are different spars. So, these are the spars that runs longitudinally, and they are basically beams. It takes a large amount of flexural load. And also if I look at a 3D view like this, then along the wing at many stations, I would say at many places across the span, there are these kind of airfoil shapes that helps in maintaining the airfoil shape, and those are called ribs, and also they give support to the spar. So, they break the span of the spar and also give helps in maintaining the airfoil shape, and those are called ribs. So, these spars and ribs are also made of CFRP, then vertical and horizontal stabilizers, center wing box, then fairings, cargo doors and control surfaces, they all have applications of composites. Fairing have both CFRP and GFRP, glass fiber reinforced plastic and glass and carbon fiber reinforced plastic. Airbus A380, we can see a model here that uses around 20 to 22% composites by weight, and again CFRP, GFRP and glare is there, mostly it is CFRP. Now, CFRP is used in the wing center box, tailplane, elevators, floor beams, pressure bulkhead and control surfaces. And glare, we have seen it, that is applied across 485 square millimeter area in the upper fuselage, and stabilizer leading edge. Now, these composites gives us around 15 to 30% weight saving. So, CFRP wing box alone saves 1.5 ton here, and glare saves around 0.8 ton if I compare with the its aluminum counterpart. Now, Airbus 380 is older version of older version than A350. So, A350 came into use at around 2015, whereas A380 was there from around 2005. So, although it is 350 and 380, but this is newer and this is older. So, we can see that in Airbus also with time composite use is increasing, not decreasing. Then combinedly it saves around 15 ton in A380. So, lower airframe weight improves fuel burn. So, with A380 approximately 17% lower fuel use is there per passenger if I compare with similar large aircrafts. Again more details can be found here. So far we talked about the large commercial jets. Now, let us see the use of composites in small aircrafts. In small aircrafts also CFRP and GFRP are used in the construction of fuselage shells and outer skin. So, it provides weight reduction of around 20 to 30% if I compare with aluminum. Example are pipistrelle virus and diamond DA20. They use GFRP for most of the fuselage components. If I look at wing and control surfaces, there are composite spars, ribs and skin. It helps in reducing weight and increasing stiffness, and it enables improved lift to weight ratio and longer wingspan with laminated drag, with minimal drag. And there are flaps, rudders and elevators which often use CFRP sandwich structures. Landing gear is a crucial component because that has to absorb a lot of shock. In landing gear there is a component called lip spring. We will see it in more details when we talk about automotive applications. So, there composites are used. So, they absorb shock load and reduce part count. Propellers are also made of composites, mainly CFRP and Kevlar. So, this is lighter and more durable than other propellers. So, because it is lighter, so it is reduce the rotational inertia. So, finally, it improves the engine response and also it reduce vibration. And not only that, composites, the property of tailoring which we can achieve through composites, which we have seen as one of the advantages, that is also exploited in design of propellers. And structural frame integration in composite airframes, the entire load bearing structure including bulkhead and stringers is made of carbon epoxy composites, and this enables monocoque and semi monocoque design with fewer joints. That is crucial. Now, let us look into the use of composites in stealth aircrafts. So, carbon fiber reinforced polymer is extensively used in skin and structure. So, the skin absorbs the radar waves. So, this contribute to stealth and low observable profile, and not only that, it helps in achieving smoother surface. So, for a stealth critical design, surface design of the surface also plays a major role, and that kind of complicated shape we can achieve with the help of composite. So, definitely it gives high strength to weight ratio, and because of that it burns less fuel. So, for example, if I can take the example of this B2 bomber, so it has 11,000 kilometer almost range, unrefueled range, because of using composite. Then as I said that shaping is important, so that is possible with the use of composite. Now comes supersonic and hypersonic vehicles. So, something which flies above the speed of sound. So, we have something called Mach number, which is the ratio of the speed of object and speed of sound. So, supersonic means it has a Mach number of generally between 1.2 to 1.5. So, at that Mach number when something flies, the aerodynamic heating takes place. So, it has to sustain enormous amount of load, at the same time it has to sustain very high heat. So, that is why carbon fiber reinforced polymers and thermosetting composites are used in non-critical areas that are subject to moderate heat. So, with advanced resin system, with the application of these chemicals, this polyamide and bisaramide, the use of composite up to 2250 to 300 degree centigrade in supersonic zone is also possible. And there are lightweight frame components like fuselage panels, fairings and control surfaces where composites are used, and it reduces the weight, and that is important for fuel efficiency and thrust to weight ratio in high speed flight. And also again the radar absorbing capacity comes into picture here. Hypersonic, so something which has beyond Mach number, beyond 5, we call it the hypersonic regime. So there is heat shielding is involved there. So in the hypersonic or near hypersonic aircraft, FRP plays a big role. It is a part of multi-material solution with ceramics and metal matrix composites for thermal protection. So thermal protection is very important here. So the solution lies in choosing multiple materials. So there are ceramics, metal matrix composites along with FRP to give that protection. Some of the examples are these. Now let us talk about unmanned air vehicles. So in unmanned air vehicle, composite is extensively used, especially in fuselage, wings, empennage and spars. And there are sandwich composites that are used. So sandwich has CFRP plates at the two top and bottom surface, at the mid it has soft core like foam or honeycomb. So this ensures high strength to weight ratio, and finally with the help of this significant weight reduction is achieved. So and with this helps us in designing a large endurance flight, which is very crucial for surveillance and reconnaissance missions. So composite UAVs often achieve 20 to 40% more range. And also again with composites we can give the desired shape, so that helps us in making better aerodynamic shapes. So it gives us better aerodynamic efficiency, and also it's in stealth critical applications like drones, stealth drones and high altitude UAVs, composites are crucial. So CFRP is often combined with other radar absorbing materials, and that gives better stealth capability. So examples are these combat UAVs like Northrop Grumman RQ-180 and BAE Taranis. Apart from that, with composites we get better manufacturing advantages. So composite UAV parts are often modular, and it allows for quick assembly and repair in the field. So methods like RTM, resin transfer molding, and autoclave curing are used for better precision. Okay, now let us go to automotive applications. First is lip spring. So we have seen the use of lip spring in landing gear also. So lip spring is basically a component like this. So it has constraint here, it has constraint here, and here it is loaded. It can be loaded in both the direction. So these lip spring are crucial for absorbing the shock or impact. So it's a suspension component. Now if we make this lip spring using composite, we can make it 70% lighter than steel counterparts. So finally it contributes to better fuel efficiency and lower emissions. And not only that, these generally suffer a lot of I would say cyclic load. So these are fatigue prone. So it improves the fatigue life. So it has better service life. And also we have seen that we can tailor the properties of composites with more control than the isotropic counterparts. So tailoring is possible here. So some of the examples are this Chevrolet Corvette C5 C6, which is a sports car in USA. So that has transverse lip spring made of GFRP. Then another application in the automotive industry is Formula 1 racing car. So here the monocoque chassis is made of CFRP. Here the main application is the benefit is due to its high crash energy. So, it can absorb more energy. So, it can keep the driver safe because of that. So, it offers exceptional stiffness to weight ratio and better ensures driver protection. And body panels and aerodynamic components are also made by composites, fronts and rear wings, nose cone, engine cover. Barge boards are made from CFRP. So, it enables in precise aerodynamic shaping for reducing drag and increasing downforce. Then there are suspension components like wishbones and control arms that are built using CFRP and CFRP aluminum hybrids. So, this reduces unsprung mass, improving cornering response and grip. So, wishbones are, these are, that is a new term here, there is a suspension arm, generally A or V shapes. So, they connect wheel hub to chassis. Then in the front and rear impact zones, CFRP is used. So, benefit is that CFRP crumble progressively, so it absorbs more energy. For example, the front crash structure absorbs around 30 kilojoule of energy in less than 0.3 seconds. So, a modern F1 car weighs around 0.8 ton and with 85% carbon composite content. So, the composite use contributes to 2 to 4 times higher specific strength than metal. Now, let us see some example in public transportation. One interesting example is this Cobra tram which runs in Zurich. So, there we use there we can see the use of GFRP interior lining panels that is utilized across the sidewalls, ceilings, vestibule sections. So, this helps in longevity and simplicity of shaping. Then this FRP is used for driver's desk back office surface. This creates robust, accurate instrument housing, and this provides high performance finish and built-in cable routing. Then GFRP seat shells are utilized in vestibules and passenger compartments for durable and easy to clean surfaces. Now, let us look into marine applications. So, these are high speed crafts where high speed vessels where composite hulls are made. So, in a high speed vessel, one example is this corvette. So, there the entire hull is constructed using composite. So, with that definitely a better advantage is we get high strength to weight ratio, and very importantly in saline water it gives very good protection against corrosion. And apart from that, the superstructure, that means the structure above the deck, they does not bear too much of load. So, they are also use FRP. So, with the help of that we can reducing the center of gravity and enhancing stability and maneuverability, that can be achieved with that. And also in sonar domes composite is used. So, because of their acoustic transparency, that means they absorb the acoustic signal, does not reflect too much of it. And for radomes also, which protects antennas without interfering with electromagnetic waves. And not only that, in very large ships which generally have steel hull, they are also in superstructure, many a times composites are used. And of course, there are composite submarines also which are there. All right. So, when there is underwater explosion, composite gives better response to the shock load. And apart from that, the modular design of interior components is possible. Cabins, panels, doors and partitions inside are often made of FRP for ease of installation, repair and fire resistance. And not only that, in these vessels, there are often the ballast systems. Ballast system means something, a chamber where we add water, that we call ballast, or we can remove water, that we call deballast, and that is generally used done for controlling the buoyancy. So, for ballast piping, sewage piping also composites are used. Then Merrill drilling riser. So, drilling riser is a kind of pipe, a pipe basically large diameter pipe. So, that connects the rig here. So, the rig is at the surface of water, and at the base there is subsea blowout preventer. So, a marine riser connects this. So, connects the rig with the subsea blowout preventer. So, this is the base from where oil is drilled, I mean drilling for oil is done, and this is the water surface. So, it connects the water surface with the, I mean the rig at the water surface to the subsea blowout preventer. So, FRP is used to fabricate the buoyancy modules or synthetic foam collar attached to the riser. So, these provide neutral or positive buoyancy, and it helps in reducing tension load on the riser system. And again the modular nature of composite fabrication comes into picture here. So, FRP riser joints and connectors can be prefabricated in modular sections, and that allows for custom length and easy transport and assembly. Wind turbine has a very large applications of composites. The main component where composite uses these rotors. So, we can see 3 rotors here, and these rotors have very complex shapes. First of all, by cross section they are airfoil, and the airfoil property also changes across the span, and not only that, these are pre-twisted also. So, with that kind of shape, composite fabricating that kind of shape with composite is easier, and most importantly, I mean if you make it using composite, it becomes lighter. So, it has less rotary inertia, so it makes it more efficient, and because it is always rotating, and so it is prone to fatigue also. So, fatigue resistance and aerodynamic performance can be achieved with composites. Now, again the composite a cross section of a wind turbine blade also has parts. So, we can see one cross section here. So, this is taken from our paper on study of composite blades. So, here we can see how composite is used in different parts of the cross section. So, spars, there are composites, the skin is made of composites. Then if I look behind here, so if I look behind these rotors, so there is a structure like this, and that is called nacelle. So, this nacelle actually has the gearbox, generator and other components. So, it is a cover to that. So, that is also made of composites for its lightweight and corrosion resistant properties, and it can withstand harsh outdoor environments. So, we can see a hub here. The hub cover and spinner domes are also made of composites, and not only that, with the use of composites, the aeroelastic tailoring of these rotor blades is also possible. So, these large diameter blades. So, nowadays we talk about wind turbine blades of length around 90 degree or even more. So, these large blades are prone to aeroelastic instability like flutter. So, and flutter is often associated with the coupling of bending and twisting modes, and we will see later on that in composites, by changing the lamination sequence, the stiffness coupling between these modes are possible. So, we try to change the lamination sequence in such a way that the flutter can be more avoided, and that kind of study can be found in this paper. Then there are several biomedical applications, orthopedic implants and bone devices. So, FRP composites reproduce the anisotropic nature of bone, and they are appropriate for bone screws and bone implants. They are employed in hip and knee joint replacements because of their high strength to weight ratio along biocompatibility, and carbon fiber composites are particularly prevalent in load bearing implants. There is applications in prosthetics and Orthotics also. So, FRP materials of lightweight improve mobility and comfort, offers customizable flexibility and stiffness for patient fitted with prosthetics, and this enables aesthetic shaping and long term durable performance also. There are dental uses. So, it is used in dental bridges, posts and crowns. Also GFRP composites provide translucency that matches natural teeth. Surgical tools also have use of composites. FRP composites are utilized for the production of MRI compatible surgical instruments. Again non-magnetic nature comes into picture here, and lightweight and radiolucent. So, this enables better imaging during operations and provide electrical insulation and sterilization capability. Spinal impacts and devices. FRP composites are employed in spinal cages, rods and plates during spinal operations, and there are other different applications also here. For example, cardiovascular devices, they also have use of composites. Then various rehabilitation devices like splints, braces, walkers and support devices, they are also we can see the use of composites basically because of its strength and lightweight. In tissue engineering scaffold also composites are used, and then in biomedical sensors and monitoring devices composites are used. Now, composites are not intelligent in its own, it has passive adapting capability, but with the use of smart sensors and actuators this entire thing can be made intelligent and smart. Let us look into some of the civil engineering applications. So, we can see a cable stayed bridge here. So, a cable stayed bridge has these A type of towers, they are called pylons, and from the A type tower we see the cables coming out, and these cables hold the main bridge deck. So, this tower, the bridge deck, and many times these cables are also made of composites. In cables generally Kevlar ropes are used. Retrofitting of civil engineering components. So, retrofitting means when we try to strengthen the structure to bring back its strength. In retrofitting, composites are extensively used. For example, in beams and girders, the exterior bonding of FRP is there to provide flexural capacity, actually to increase the flexural capacity. So, U wraps are used to enhance the shear strength. Columns, FRP wraps are there in columns, so that increases the axial load capacity, and it is very effective in seismic retrofitting. Then in slabs and floor system, FRP strips or laminates are bonded below to prevent sagging and cracking. Walls and shear panels also have the use of composites. In bridge decks and girders also these composite reinforcement are used for retrofitting, and then even in historical and masonry buildings also retrofitting is done with the help of this CFRP and GFRP. So, these are some of the standards which are generally followed for this kind of retrofitting. There are many standards, just 3 is mentioned here. In pipeline, composite is often used. So, pipeline body, the main the pipeline body is made of composites. So, the main application of FRP is in the pipe wall itself, which is made of glass fiber, usually E-glass, in a thermosetting resin, and it is made using methods like filament winding, centrifugal casting and hand layup. Now, FRP pipe generally have 3 layers. The inner layer, that is in contact with the fluid. So, that is made resin rich because it has to it has to offer high corrosion resistant and smooth surface. Then there is a structural layer which is the main load bearing layer. So, it is more fiber rich. So, usually 55 plus minus 55 degree helical angle is given. So, to give offer hoop strength and longitudinal stiffness. So, we know that if we look at a cylindrical section like that, if we look at the cross section, we get stress around this, and that is called hoop stress, and we get stress around this direction, that is called longitudinal stress. So, that is why this angle of this helix is very important, so that both the requirement can be catered for. And there are outer layer which is a protective layer that is exposed to the environment. So, that can have UV resistant coating and resin rich surface. So, it has to protect the entire pipe from abrasion, moisture and environmental degradation. Joints or fittings are very important in these cases because it has to provide leak tight seal. Also the strength continuity has to be maintained. So it employs various fittings and joints such as bell and spigot joints, threaded or flanged connections, adhesive bonded joints, overwrapped joints, and so on. Then in a piping system we often get these kind of connections, T, elbow. So they are also made of composites. So it has to withstand the stress concentration that may occur in these joints. So there are various techniques that are used to fabricate these composites. And then there are supports and saddles. So FRP pipelines are supported using engineered saddles, clamps, and hangers. Support design considers the flexibility and expansion characteristics. And protective coatings is given to these pipes. So FRP pipes sometimes have thermoplastic inner linings for enhanced chemical resistance. Then let us come to another application, military protective gear. So military protective gear composites are used mainly because of its impact resistance and lightweight. So helmets are made of aramid fibers or carbon fibers. So it gives better ballistic protection with significantly less weight. So we get more protection, but with more comfort. And then there are shields that are made of composites. It typically consists of aramid, glass fiber, and polycarbonate. So these are used by military and riot police for protection from projectiles, debris, and impact. And also it gives partial transparency when used with FRP laminated polycarbonate for visibility and protection. Body armors also have great use of composites. So bulletproof vests and inserts. So layers of aramid fiber reinforced polymers and ultra high molecular weight polyethylene are used here. So woven FRP panels allow for flexibility in torso movement. So we can see that when we design this protective gear, it has to be less weight, it has to give enough protection. At the same time, it should be comfortable when we wear it. So the design is challenging here, but with the help of composites that can be done. Now let us talk about some of the future trends. So design of structures and systems capable of operating in severe environments. So high temperature applications, we have seen part of it. Smart composites, if we can add active or passive sensors, it can be made smart. Then we can have nano fillers, and that can increase its that can increase its strength and make it multifunctional. So that can be used for energy storage, load bearing, and thermal management. And then there are intelligent fabrication process also. There are significant developments being done for affordability, functionality, and reliability. Self-healing composites, that is interesting. So these are generally composites which have micro capsule and vascular network that are used for self-healing. And also 3D printing and additive manufacturing is there. So there is significant development in composite fabrication also with the help of these advanced techniques. So we can see that the possibility is enormous, but for every design proper analysis is needed, and that is this course is about. So in this course we will talk about the mechanics of these composite materials, the plies and the laminates, and then we will go to the analysis of these composites. So with this I would like to conclude this lecture here. Thank you.